Today I wanted to focus on erosion. And one of the reasons for this is that these are, I think, some of the very simplest arguments for the age of the Earth out there, that you don't have to actually be a geologist for it to make sense. And it's coastal erosion, basinal erosion, and paraconformities, and I'll explain the last two. So coastal erosion rates, if you look at the coastal erosion rate, the West Coast, it's about 20 centimeters per year. It depends. It varies a lot. In some places it's several meters per year. Some places it's slower than that. But there's always a bit of coastal erosion. And even when you get aggradation, even when you get sand deposited on the coast, it shifts and then it gets eroded away again. And it just over a long period of time, it just gets eaten away slowly. So North America, West Coast, about 0.2 millimeters per year, 0.2 meters per year. North America, East Coast is about a meter per year. That's the last figure. The last figure I pulled off of the top Google search was 1.2. Before that, it was 0.8. Average is about a meter. If you look at the lighthouse data, they've had to move about a half a dozen lighthouses on the East Coast to save them from getting eaten by the encroaching surf. And every time they move them, they give them another 70 or 100 years of life. And they know exactly where the coast was when they built the lighthouse. They know where the coast was when they decided to move the lighthouse. And it averages about 2 feet per year of erosion. And I would just like to point out that no one has ever had to move a lighthouse out closer to the ocean to keep it useful. So just some quick math. 4,500 kilometers is 4.5 million meters. If the total erosion is about a meter per year, that's about 4.5 million years of total erosion before it's all gone, right? Does that make sense? That's the very basic argument. Africa, West Coast, 1.8 meters per year. Again, that's not going to be for the entire coast probably. And we probably don't have as good of data tabulated for Africa. Britain, 0.4 meters per year, and you can see it's a bigger problem because it's only 500 kilometers across. So Britain would be gone long before North America. South America, 500 kilometers per year. Now 5,000 kilometers wide, and here's the coast of Argentina. So you can see they've done a really nice job of kind of grouping all the data. So you can see that there's a lot of it where 0.4 to 0.7 meters per year, a little bit where it's greater than 1.3, which is kind of crazy, and then a little bit of accumulation, 0.5 to 2 meters per year of accumulation right there. But again, that's going to shift over time. So one question I have is, if all of this erosion is happening for millions of years, why do the continents still fit together? Why do they still look like they fit together in Pangaea? Does that question make sense? If you look at how, in other words, like if you look out to the very edge of the continent, this is oceanic crust, and it's thin and it's made out of basalt, and this is continental crust and it's thick and it's made out of granitic material. And so the reason the continents are higher than the bottom of the ocean is because of the isostatic, it floats. They float in the mantle, basically, and they're a lot thicker. So this is really the edge of the continent. That's only 30 kilometers out off of the coast of Liberia. And if you back away from that's pretty consistent all along the West African coast. Now there's a lot more here because that's where a river comes out, so it's been dumping sediment for a while. If you look at the east coast of North America, you got about 100 kilometers of, out to the edge of the continent. If you look at the west coast of North America, you got about 20 kilometers. Now, something I'd like to point out, remember that it was 0.2 meters per year on the west coast and 1 meter per year on the east coast. If you multiply 20 by but I mean, if you divide 20 kilometers by 0.2 and you divide 100 kilometers by 1, you end up with 100,000 on both sides. So it looks like kind of ignoring sea level rise and anything that might complicate the data. It looks like you get about 100,000 years of time to get that much coastal erosion, and that does not account for catastrophic sea level rise or any like if there was a period of Earth's history where there were a lot of hurricanes or something like that, it wouldn't account for that. Okay, basinal erosion rates. So how fast is the continent getting eroded down from the top? Different question. So the Amazon River dumps about a third of a cubic kilometer of earth into the ocean every year. Yeah, and it's probably more than that. It's probably a lot more than that because that doesn't include dissolved material. That doesn't include a lot of the material that gets kind of just pushed along the bottom of the river by the water. All rivers in the world, they figure it's about 5.6 cubic kilometers. And again, I think that's a very low number. Because of this next number, notice that the sediment that collects behind dams and reservoirs each year is 50 kilometers cubed. So they figure that dams and reservoirs lose about half to 1% of their capacity every year from all the sediment that gets dumped into them. And so sometimes they'll try to dredge it out, but dams have limited lifespans because of that. And if you look at so we have 124 million cubic kilometers here of total volume of land on Earth. And if you divide that by 50, what do you get? It's like 2.4, right? 2.4 million years for all of the land on Earth to get trapped behind the existing dams and reservoirs. That's part of the reason I think this is too low. I don't think this is a high enough number. The other reason that I think that's too low is because what they do is in the river, in the water column, there is what we call there's bed load and there's suspended load. So suspended load is the grains of sand and stuff that is carried by the water and like up in the current, and then bed load is the part that gets rolled along the bottom of the river. And I've seen estimates where they've said 10% of the load is bed load. When I'm doing experiments, I can see that much more than 10% is bed load. And my experiments are not going to be analogous to like the Amazon River, for example, but still I think they're really underestimating bed load. And I think that's part of the reason why this figure is so big, because this is an actual measured figure. This is something engineers have to deal with. Now it gets interesting when you look at specific areas of the Earth. The volume of New Guinea is 524,000 cubic kilometers. And the rivers of New Guinea, it's got 250 rivers that dump more sediment to the ocean than the Amazon does. So if you divide this value by this number, or a bigger number than this, you get about 1.6 million. So in only 1.6 million years, the rivers of New Guinea would have flattened it out. Now again, that doesn't account for, as it gets flatter, the rate of erosion gets slower. So there is that factor, but that's not going to give you tens or hundreds of millions of years of more time. And so one question is, well, maybe there was a ton of sediment that got eroded away over the time that we've had so far. We looked at this last week, and we have about a mile here, and notice that these layers go all the way up. This is Grand Canyon. These layers go all the way over to here. We got Zion Canyon, Bryce Canyon, and then right here we have, this is at like 12,000 meters worth of sediment deposition total. And over here we've got maybe is that just 4,000 meters right there of sediment? So if we have a total of 8,000 meters washed out of here, that's a lot of sediment. That's a lot of cubic kilometers of sediment. But we can look at the ocean basins and see that there is something like 2 or 3 times the amount of sediment in the ocean than is the volume of the land so far. And so again, it doesn't, like, the time's not there. We don't have time for all of that. There isn't time, there hasn't been, like, the sediment is going to the ocean so fast that there hasn't been time for millions of years, too many millions, some millions of years, but not too many millions of years to have passed since the whole thing started. This is something that happens to geologists all the time, where you have, like, so this geologist standing here looking at this outcrop, and she sees a nice sharp line right there. And this geologist is looking over here, and he sees the same outcrop, but with a different bed inserted in there. And so this is called a paraconformity. The difference between, these are all conformities. In other words, they all fit together very nicely. This one fits nicely too, but we can look over here and say, okay, now something's actually missing right here. And sometimes what is missing is fossils. Sometimes what's missing is another actual sedimentary layer. And so these are called paraconformities, and it happens, like, it's a very, very common feature of the geologic record, where you get paraconformities where there's supposed to be 6 million years in this gap right here, but you don't see any erosion. You don't see, it's just a flat layer. You don't see deposition or erosion on that flat layer. It's supposed to be 15 to 40 million years right here. This is the Shinnerup and the Moenkopi. This was the Coconino. You can see the crossbeds in the Coconino, and then the Hermit Shale right here. And this is Grand Canyon. Moenkopi, Shinnerup, and sometimes you can actually see load casts from the Shinnerup into the Moenkopi, where you can see that this was mud. It was soft mud, and this stuff, the gravel of this formation got kind of pressed down into it, and then when it pops off, you can see the cast. And so again, but there's supposed to be 15 to 40 million years right there in that gap. And this one is this gap right here between these two sandstones. So this is Shinnerup again, but this is Deshay right now. So there's several layers missing in there, layers that appear elsewhere, but they're not here. And there's supposed to be 50 million years right there. Now this contact is not as flat as the other two that I just showed you. There is a bit of erosion at that contact, but I would say definitely not 50 million years worth. And this is just to show you kind of how big the problem is. All of these black areas are, the white areas exist. These are rock layers in the Colorado Plateau, all the white layers. But the black layers are rocks that perhaps should be there but aren't. Just looking at the time. In other words, the Lynch Muav Tapites, it's supposed to be 500 million years. That contact is supposed to be 500 million years old, but the red wall didn't start getting deposited until almost 450 million years ago. So we got that 50 million year gap right there, and all of these other, I don't know, does that make sense? Okay, so a little bit about, I would say that the biggest piece of feedback I've gotten on this from professional geologists is you are not using uniformitarianism correctly. In other words, I'm using modern rates, extrapolating the modern rates back in the past, and they would say, but we know that the rates haven't been constant. And I would say, yeah, I agree. They haven't been constant. That's not what I'm saying. What I'm saying is that if the rates were even close to the modern rate, the time scale doesn't work. That's my argument. My argument is not that the rates have been constant, but rather that even if they've been within an order of magnitude or even 3 orders of magnitude, even if they've been 50 times slower in the past, it still doesn't work. Another argument that I've gotten has been Well, this stuff is pushed up from beneath as things get eroded off of the top, and more gets pushed up from beneath. And so that's why we still have continents here. And so you can have this cycle, kind of never-ending cycle of getting pushed up from underneath and eroded off the top. And so my question there is, why does the entire geologic column still exist? It gets renewed from beneath and eroded off the top, but the top has not been eroded off even once yet. I don't know anybody who would argue for very strict uniformity of rate, but we would argue for I mean, I do know many people that would argue for uniformity of process. And so in uniformity of process, you're not going to get extremely different rates. And one of the problems I see also is that one of the reasons given for, say, Coconino or Navajo sandstone being mobile and wet, or not being like locked down with roots, is because grasses and flowering plants hadn't evolved yet. But that would just increase erosion. It should greatly increase erosion if we didn't have grasses and flowering plants, right? I have seen 2 peer-reviewed papers that did deal with this. One paper said bacterial mats. Like, I don't know. Like they were grappling for something, and they're like, bacterial mats? I don't know. To stabilize everything. And then the other paper said the erosion rates, they were talking specifically about Everest, the erosion rates were 50 times lower in the past. And they just threw that out there and gave no mechanism and no explanation. And so I'm glad that he realized what the problem was, that he did the math, that he was aware of what he was saying, and he's like, it must, somehow it was 50 times lower in the past. Now I will say also, like back in the 60s, there were people that noticed this problem with the basinal erosion. They noticed it and they brought it to the attention of the scientific community. And several of these guys said, like, look, we have a problem, and and other people I think saw it and was like, okay, that is a problem, but I don't know that anybody worked on it after that.
Yeah, just ignore it.
Like sometimes problems are too big and it's easier to ignore them, I think. Yeah.